Hi, I'm Tracy Lauderette, call sign Jackie O, Colorado's First Lady Fighter Pilot. We're here at Wings Over the Rockies Air and Space Museum in Denver, Colorado. We're getting an inside look at the world's largest operating aircraft, the Stratolaunch Roc. Roc is key to expediting hypersonic flight technology through testing. With a wingspan of 385 feet, this thing is massive.
We had started with a napkin and built an airplane.
What Roc is doing is transformational for flight testing.
We're continuing to add complexity.
Now it's time for the mission.
If you are launching a hypersonic vehicle from the belly of an aircraft, you have seconds for it to work correctly.
When you're going something like 3,000 miles an hour, the airplane gets hot.
The first time you watch it take off, you can't help but feel like, oh, is it gonna be okay?
It's really a renaissance of hypersonic flight.
Release.
This is going to be cool. It's time to go behind the wings. As the sun rises over the Mojave Desert, a one-of-a-kind aircraft is instantly identifiable. Dual fuselages, connected by a single high wing, longer than a football field, and a payload that with each flight is advancing the United States hypersonic flight test capabilities. Stratolaunch named the Roc for legendary bird of prey large enough to carry elephants. Roc carries the Talon A reusable hypersonic aircraft that launches mid-air from between the Roc's dual fuselages. Hypersonic flight, defined by speeds greater than Mach 5, remains one of aviation's most elusive challenges. When traveling at 5 times the speed of sound, an aircraft's energy begins to affect chemical bonds. A realm where air becomes fire and the laws of physics wage war against human ambition.
Hypersonics is not new. We've had systems flying at hypersonic speeds for a long time. We had a flight back in 1959, the X-15.
Early on this Thursday morning, the B-52 carrier takes the X-15 out for its maiden powered flight.
We flew over Mach 6, and since then we've had a lot of hypersonic systems, obviously the space shuttle, the lunar capsule, Apollo. We've been flying in the hypersonic regimes for a while now.
Back in the 1960s, the United States was a groundbreaking country in hypersonics with programs like the X-15. 199 flights, over 100 of those flights at hypersonic speeds. But then there was a bit of a lull in this country, around the globe, in terms of advancing hypersonics capability. Now it's come back because there's lots of interesting applications. You can look, of course, at the civil, cargo transport. Obviously, there's military applications. Everyone is realizing the benefits of what hypersonic flight can do in terms of going through the atmosphere at 5 times the speed of sound. A variety of countries, including ours, are pursuing that capability.
The new thing is that these new hypersonic missiles that we're talking about are different in that not only do they fly at hypersonic speeds, but also they fly in a different trajectory. The traditional hypersonic missiles, right, like an ICBM, intercontinental ballistic missile, it flies hypersonically, right? It re-enters at Mach 20 or above. However, it doesn't maneuver once they re-enter the atmosphere. So the new hypersonic missiles are maneuverable. You can use them to change the target while they're in flight. You can potentially improve their accuracy. You can potentially retarget them while they're in flight. In terms of technology, I would say, you know, the US is probably a little bit ahead of everybody else, but in terms of systems having been deployed, I would say that the US is behind. China and Russia are ahead. In order to be able to develop these hypersonic vehicles, we have to do a lot of testing. We have to do ground testing, which use wind tunnels or hypervelocity test tracks. But also you want to be able to flight test them, because flight testing is basically the final say in terms of what your environment is and in terms of what you're going to be seeing, right? That's the ground truth. One way to fly them is to build a vehicle, launch it, and test it. But that's very expensive. Another approach is what Stratolaunch Roc offers. It's a hypersonic testing platform.
How would you describe this moment in hypersonic flight?
It's really a renaissance of hypersonic flight. Our hypersonic program is really making a lot of great strides and quickly. So we've done a number of flights now, proving out various aspects of the system. We can get through some of the initial shocks on the vehicle as you get through the transonic, that Mach 1 regime. Carrier aircraft, Roc continues to perform quite well, and now we're continuing to add complexity. We're going to higher altitudes, we're doing more complex propellant management on board our hypersonic vehicle, and what that allows us to do is push to the outer edges of the envelope. Today we can go Mach 3, tomorrow we can go Mach 6, we can go anywhere in between.
Why are we even testing in hypersonics? What's it all about?
Our goal in testing in hypersonics is to create certainty about the technologies that we are developing. We have a great ground infrastructure here in this country, but they are not quite the actual flight environment. Still a lot that we're uncovering in the physics in terms of the thermal, accelerations, control of the vehicle, and because of that, we need to demonstrate that in the flight environment so that when we want to call upon a hypersonic flight system, you want to know it works. The secret sauce for us, it's the ability through reusability to have a high flight cadence. The Pentagon has put out a call to do hypersonic flight testing every week. It's really been exciting seeing Roc from its mid-construction days now to releasing payloads. So a lot of credit to the original equipment manufacturer, Scaled Composites, who actually built and flew Roc for the first time.
Before we see this jet in action, let's look at why it was produced and what it took to turn this dream into reality. Whoa! Are you kidding me? Scott, I've seen a lot of airplanes in my day, but this design idea is like nothing I've ever seen. Tell me about that initial team.
So it really was a great team. It was assembled at Scaled Composites, who collected engineers, technicians, fabricators, all with an ambition to build the world's largest airplane. They approached the problem with always the goal of how do we fly. So this airplane started as a napkin sketch just like any, and Bert had hundreds of different airplanes. And it took a couple years to gain funding from the idea to, hey, now we're actually really gonna go build this airplane.
The first challenge was going from an idea on paper to an aircraft that actually flies. Chantel, you've been here longer than this gigantic hangar has been here. Take us back to the early days.
The first thing they had to do was build the hangar. This is actually the largest free span hangar in the world. So it was kind of an engineering feat just to design the hangar before we actually built Roc. The first thing they did was they built a bunch of scaffolding and started the spars. So the first thing was the spar that went from wingtip to wingtip. A lot of people think it's two wings put together. It's not. It's one giant wing that goes all the way through the two fuselages. They built the fuselages around the wing. So it was kind of cool to come in and the wing would just get bigger and bigger. And then they came in and the fuselages were put together. It still takes my breath away working on this thing.
Scott, what were some of the thoughts that went into coming up with this crazy looking aircraft?
You have a ton of requirements. The one key requirement was to carry and drop a 500,000 pound rocket. So the original mission for the airplane was satellite launching. So a 550,000 pound rocket to be able to leave Mojave, fly 1,000 miles away, launch a rocket and a satellite, and then fly back to Mojave. When you look at other airplanes throughout history, you know, they typically all carry a mast. Passenger airplanes carry a mast in the fuselage, kind of the center of the plane. When you drop the mast in flight, you naturally want to put the mast in the center so that when you drop it, the airplane doesn't roll or pitch or maneuver, right? So that drives a mast at the center of the wing.
Scott, this is the biggest wing I've ever seen. Is there another wing like this anywhere in the world?
No, this is the only one. In fact, most everything on this airplane, this is the only one of. So it really is a typical airplane wing. It's made of I-beams. An I-beam's got a web, a top cap, and a bottom cap. Our center portion of our wing has 4 spars, 8 caps. Some of the caps are as heavy as 19,000 pounds and 265 feet long. And eventually we get to ailerons. There's 12 ailerons on the airplane, 6 per side. They're all hydraulically driven. And on top of 12 ailerons, it has 14 flap panels, 28 actuators on the flaps. We didn't want to invent anything. So the actuators on the flaps are actually the Boeing gear door actuators.
Here we are at the tail, but the tail's way over there too. Why on earth are these tails not connected?
If you're designing an airplane, you need to know how much load goes through the wing. If you connect the tails, now you need to decide how much load goes through the tail versus the wing, and it becomes an iterative problem that takes longer to solve. The wing takes all the twist. Taking the twist through the wing is a fairly standard problem to solve.
Easier to build, probably easier to fly, but still, One of the most bizarre airplanes I've ever seen.
It's a crazy airplane. Let's go look at the rest.
All right, let's go. Scott, I thought you said meet you at the cockpit.
I am at the cockpit.
How do you go from those ideas on paper to this incredible airplane we're looking at now?
So the requirements grew to build a 385-foot wingspan airplane with 6 engines, 2 fuselages. That was a lot of invention. After that, we tried to keep the invention small. So we didn't want to invent new landing gear. We didn't want to invent new wing construction methods. We tried to focus on how to build big and how to build fast.
Scott, this airplane looks very unique, but on closer look, a lot of the parts look super familiar.
When we laid out the program, need engines, hydraulics, landing gear, we took a look and said, where do we get all these? We could make our own specs to buy new landing gear. And really, a lot of the 747-400 parts, such as engines, pylons, landing gear, really kind of fit our bill pretty good.
Across the way from Stratolaunch is the Mojave Air and Spaceport Boneyard. Stratolaunch incorporated a lot of different kinds of aircraft in the design of Roc. Well, they brought some of those extra parts here to the Boneyard.
To build this airplane, we bought 2 United 747-400s, flew them into Mojave, and then led a team of engineers loose and said, what do you want? We used the transparency, so the canopy glass, a lot of flight control parts, hydraulic actuators. It doesn't reuse the 747 as an airplane, but it reuses a lot of off-the-shelf components that are used on the 74, as well as other things. There's business jet, environmental control systems, there's custom stuff. What we tried to do is not make new when we could buy something that was already available, and that both led us to a much lower cost as well as a much shorter development time. We were just putting less energy into the whole system. We were reusing.
One 747 wasn't big enough, so you needed to bring in 2 to source the parts. I mean, we're looking at what, 6 engines on this guy?
We bought 2 airplanes. We got 8 engines, so we have some spares. So it uses 6 engines. They're 56,000 pounds of thrust apiece, which is the highest thrust airplane.
So you take the parts you need off of those 2 747s and just ship the extras to the Boneyard?
It feels wrong to take 2 flyable airplanes, but we got a lot of parts out of them, and they went off to the Boneyard when we were done.
So Roc was built, and then you face your next big challenge, getting it outside and airborne. Talk to me about some of those challenges.
There's a few steps to get there. We, of course, went through a bunch of engine runs and taxi testing, and there was a whole bunch of testing that we had to do before we flew. It's different than any other airplane ever built. The stance of the gear is like 95 feet, so we can't really go on a lot of taxiways. The pad was kind of built for the size of Roc, and we kind of realized right away it was going to be kind of difficult to tow. Instead of using like one tug that steers to control the movement of the airplane, we have 2 tugs, and they steer by speeding up or slowing down. The very first time it rolled out, it was just an amazing experience.
So Scaled had a motto of test early and test often. The first time the airplane came out of the hangar was for a field test. That meant the structure team, the landing gear team, other teams had to get their systems just far enough along to support that test.
What kind of milestones did you have to hit?
So one of the big milestones was to do a taxi test, and we learned a ton just going 20 knots. And then we built up to 30 and 40 and a little over 100 at some points just in a taxi test. Even getting to a point on the runway where we intended to go down the runway with the main gear on the runway but lift the nose. And that was the first time we started to see aerodynamic influence on the airplane. How effective is the elevator? So after we made it through our test matrix, ending at high-speed taxi, we were ready to fly.
This is the part I've been waiting for. Let's see this thing fly.
The engineers do all their analysis and they say it's going to be okay, but the first time you watch it take off, you can't help but feel like, oh, is it going to be okay? We're really excited about what we're going to do. There might be a little bit of nervousness of just, it better go good.
Airspeed's increasing. Okay, rotate to 10 degrees.
The takeoff, a lot of people are watching. I care a lot more about the landings because that's the more difficult process.
First flight was amazing and nerve-wracking. The whole purpose to fly the airplane was to get enough handling qualities data to let the pilots fly it enough so that they had the confidence to land.
The landing was where I was just relieved. We had it on the ground in Mojave. The first flight was a great day.
After it landed, it was really rewarding to know that we had started with a napkin and built an airplane.
You'd come so far, but now it's time for the mission. Dave, you're the senior test pilot here. What does that job look like?
Job involves working with teams to get this large aircraft and its payload airborne and to do the mission. Obviously flying the airplane, but also designing the tests, making sure we can do it safely.
There's nothing ordinary about this airplane. Can you give us a little bit of a tour here?
It's a twin fuselage airplane. We're in the right fuselage. The flight controls are pretty conventional. This is a yoke out of a 747. We do have 6 throttles, but you normally have them all in your hand. So unless there's something wrong with one of the engines, it acts like one throttle. It does not have any autopilot or automation, so someone has to be flying it all the time.
When you're flying Roc, I mean, it's an incredible aircraft, but you're not just flying Roc. You have a whole nother aircraft out there in the center line. You have Talon. What does that look like when those missions happen?
So very choreographed with several interacting teams to get both aircraft off. Once we're airborne, we've been launching Talons over the water off the coast of California, and then we climb up and launch Talon.
To get a better sense of what it's like to fly Roc on a hypersonic test mission, we flew the Roc simulator.
All right, we're going to do takeoff. Tracy's going to fly it, and you can start slowly advancing the power.
6 throttles, a little more than the one I'm used to.
So takeoff's pretty conventional. We track down the right-hand side of the runway. All right, we're going.
She's a beast.
Rotate speed where we get airborne is about 134 knots. We climb out about 155. We cruise around about 160 to 170. Landing speed's usually around 130. So we would be climbing out to fly out over the ocean to launch Talon.
This is a handful of aircraft to fly, and this isn't even the coolest part. Flying the world's largest jet, dropping a Talon that's going to go hypersonic, coming back and landing, all in a day's work. You're able to take such a complex design and make it super friendly for the pilot. I climb in the cockpit and I can fly the airplane, and I don't know I have all those flaps and all those ailerons. It's just flies nice so I can focus on the mission.
This is a model of the Talon A, and it is our reusable, rocket-powered, hypersonic robot plane. It is going to allow us to repeatedly and reliably do hypersonic testing. It's going to get launched off of Roc, zoom out over the range, come back in after the rocket motor uses up all the propellant, land, and then we will rinse and reuse it after that.
So this Talon is a lot faster than the T-38 Talon I flew way back in pilot training. Can you walk us around?
Sure, I'd love to. So here at the nose, you can see that it's made up of a number of tiles. These are very similar to the tiles that are on the bottom of the space shuttle because this is one of the hottest parts of the aircraft. When you're going something like 3,000 miles an hour, the airplane gets hot. As we go further back, more access panels where we can store payloads or do the maintenance work we need to do to get it ready for its next flight. This white surface is a felt insulator that helps to keep the structure inside the aircraft cool enough that it doesn't have any issues. But back here is cooler than the nose where we have the hard tiles. We can also put things at the tail end on the control surfaces, and they're made out of a high temperature metal called Inconel, and those get very hot because they stick out in the airflow. And so depending on what you're looking at, maybe you want to test a thermal insulation, or maybe you want to test something that gets really, really hot and see how it responds as a material.
So how do the flight controls work on this aircraft without a pilot?
So the aircraft is fully autonomous. We've developed a flight control system, an autopilot if you will, that we program to guide the airplane through its trajectory. After the engine is extinguished, the aircraft will glide back in and land like any other airplane at a nearby airport.
What on earth is powerful enough to get us up to that speed?
Let's go take a look at the tail.
All right.
The rocket motor starts about here, where the tail of the aircraft flares out, and it's only that big. It's a 5,000 pound thrust rocket motor from our partner Ursa Major. It's reusable, and we run it off basically regular jet fuel and liquid oxygen.
At Ursa Major in Berthoud, Colorado, the rocket engines that power the Talon A are designed, built, and tested. The engine that powers the Talon is known as the Hadley. There's a lot of power in this little package. Is this really it? Is this the Hadley?
This is a Hadley just like the one that flew at Stratolaunch. So we're standing in the assembly line for our Hadley engine. This was our first product. This is actually the product that took us from space to hypersonics. While this is the assembly line, this is where all of the engines are hand-built. We have engineers that are designing or looking at test data. We have about 100 yards from us a facility where the engines are tested. We actually fire every engine before it goes to a customer.
Talon A is designed to be reusable, hence the Hadley rocket engine is also designed to be reusable. How does the reliability play in?
We think about reliability of an engine kind of in two paths. One is, can the engine be reused many times? And Hadley was designed to be reused probably for more missions than any other rocket engine flying today, in large part because hypersonic missions like Stratolaunch need a reusable engine. But reliability also means how safe and usable is the engine. And on a vehicle like Talon that's flying underneath Roc, you require a high level of reliability to ensure just safety and handling is part of the design as well.
What's so significant about being able to finally test regularly in the air?
You learn a lot about your engine in any flight testing. Whether you are launching from the ground, you're in vacuum of space, or you're in the atmosphere, you learn a tremendous amount. The more you fly, the more data you collect, the more you understand how your engine operates on the ground versus in these environments. With this hypersonic test flight specifically, launching from the air posed an enormous challenge. A liquid rocket engine likes to be very stationary, very stable when it ignites. So igniting on a hypersonic vehicle after it's dropped from a carrier aircraft should help improve hypersonic engines. It should help improve our space engines in the future. There are two big differentiators to what Stratolaunch is doing with both Roc and Talon. Roc acts as a launch platform for hypersonic test beds. If you think back to the X-15, America's first kind of hypersonic aircraft, there was a pilot in it. It was an extremely kind of tenuous and dangerous flight operation. Talon is unpiloted, it's automated, and it's reusable, which is a really big deal in hypersonics, where if the purpose is to increase the cadence of flight testing, driving down cost with reusability will be transformative.
Your team poured all this time, effort, and energy into diligently preparing for this very first launch.
Any first test flight, you expect some hiccups. You expect the priority of the mission to be learning, not a total mission success. If you are launching a hypersonic vehicle from the belly of an aircraft, you have seconds for it to work correctly. So you need to really understand how that engine works, how the vehicle interacts with the engine, and ensure that everything from ignition to power ramp to maneuverability is going to perform as expected.
There is a lot that happens on launch day. There's a lot that happens in the couple days prior to launch day to prepare both vehicles. Launch day, we come in very early. We have a briefing. We have test cards or procedures that are on our kneeboard, and we run through those. The aircrew go out, the airplane starts pre-flighting. The mission control room goes to the control rooms, and they start setting up.
The Talon program, we've done this dance a few times. We did a lot of practicing, so it's very coordinated. Everybody knows exactly their place. We're very focused on what we're doing. We all know what we need to do, and it's a very professional attitude in the beginning.
So much prep goes into launch day. What's it like here in mission control?
The team is ready, they're focused, they're staying calm, but they understand what they need to do to enable this moment. There's a lot of nervousness, but then also has that natural tension of a big moment, and everyone is really understanding what we're about to do. And so this team is focused on the data, making sure that everything looks ready for our missions and our release.
System 1, armed. Looking for data. Good data. Good data.
It's a big team. We take off, we go fly out to the range. The control room's watching a lot of the parameters that we can't see in the cockpit. They're kind of responsible for the mission overall. We're responsible for putting the airplane where it needs to be. And if everything goes right, we'll launch Talon and have it go Mach 5.
5, 4, 3, release.
When the flight test engineer triggers the explosive bolts, the vehicle is released.
Good release.
Watching it actually drop and drop clean. All of us just burst into applause because it's just, you can't contain it.
Ignition.
Everyone looks forward to their first flight, but to actually see the engine light, to see the vehicle operate, to see a flight, that moment was probably the most exciting moment in our company's history. Obviously, what Roc is doing is transformational for flight testing. It takes up what a launch pad traditionally would be for a hypersonic flight vehicle, for a space launch vehicle, and with more capable, more reusable engines, you just start to see this new era of vehicles be flown, reused, much more of a daily operation than what space has been in the past.
By using the Talon A, you can test components of a hypersonic vehicle without having to build a full hypersonic vehicle and test it. By testing these components, you can improve the design of these components, and by the time you integrate a whole vehicle, you've already tested some of these subsystems under the actual hypersonic conditions, so you have a higher probability of success.
From the original design on a napkin to now creating this operational aircraft that plays a major role in hypersonic testing, where do we go from here?
Every flight we do, we learn something new. We don't know exactly where it's going to lead, but we are confident that all along the way, we're going to continue to push higher, faster, and farther for a body of knowledge around hypersonics.
There is a lot to learn. Doing this autonomously, doing this repeatedly, building up that high flight cadence, there's just a lot of areas still to explore in hypersonic flight.
It's an evolutionary process. We've learned a lot, we know a lot. Now it's a matter of just implementing and improving our understanding and developing designs and vehicles that meet the goals that we have. In the long term, we're probably going to be able to develop these unmanned hypersonic aircraft. Really long term, potentially go to commercial airliners.
As hypersonic flight becomes faster and more maneuverable, repeatable flight testing will play a key role in better understanding and advancing this cutting-edge realm in aviation. We'll see you next time on Behind the Wings.